we're given an open set of Rn and a change of variables g, okay? And we're requiring that g is what's called a C1 diffeomorphism. So let's just explain what that means. So C1 diffeomorphism. So if I look at g, it's a mapping from omega into Rn. And omega is a subset of Rn. So it's going to take, let's say, a point x1 through xn, which I'm going to call x. Okay, so the vector x. And it's going to send it to g1 of x, g2 of x, etc. down to gn of x, right? Let me just. So we have n component functions, and each of these component functions depends on, like, g1 depends on x1 through xn. Right?
Yeah.
Okay, so we have, that's our setup with our map G. Then for it to be a C1 diffeomorphism, we're requiring the two properties. So first of all, we want G to be injective. Are you familiar with what that means?
No.
So that means 1 to 1. 1 to 1. Okay? So we're requiring that G is 1 to 1. And then secondly, we're requiring that the differential, let's say dx of G, is invertible. Okay? And this is the Jacobian, which is the matrix of partial derivatives. So this is like partial g1 over partial x1 all the way through, and then this should still be g1 of partial x n. Yeah, I believe this is correct. Yeah. And then this is going to be partial g n over partial x1 through partial g n over partial x n, okay? So this is, and of course these are evaluated at the point x, okay? And so what we're requiring here is that, so C1 means that all of these partial derivatives exist and they're continuous. So all the partial derivatives of g are continuous, of the component functions are continuous. And furthermore, this Jacobian matrix is always invertible. So that is equivalent to saying that the determinant is non-zero. And what that means physically is that G is not destroying any volume, right? If I look at a small piece of volume, G is going to distort that small piece of volume, but it's not going to break it apart or pinch it or like destroy its volume, right? Okay, so that all makes sense of this assumption here, right? Now, G is, we're thinking of G as like some sort of change of variables, okay? So let's start off with an example maybe of polar coordinates, just to see what this might look like. So if I look at polar coordinates, then let's just do 2 dimensions for now. So let's consider an r theta plane parameterization, and then I want theta to run from, let's say, 0 to 2 pi, and r to run from, let's say, 0 to maybe capital R. Something like this, okay? All right, so the idea is that if I define this G to be the map r theta gets sent to r cosine theta, r sine theta, this is the map G, right? Then what G is going to do is it's going to map this box into what? What will the image be?
Yeah, so like Actually, I think I need to. So theta 0 to 2 pi. So it's circle actually.
Yeah.
Yeah.
Right.
And then larger.
Yeah. So it's going to map it into a circle of radius r, exactly.
Yeah.
And we need to be a bit careful because we want this to be an open set. So let's make sure that we don't include any of the boundaries here to this box. So we're not including any of the boundaries of the box.
Yeah.
And that means we're not including the origin of this circle.
Oh, okay.
We're also not including its boundary. And then we're also missing the line at theta equals 0.
Oh.
Right? So we kind of have this picture here. So it's almost taking this, it's taking this, so this line here, for example, this horizontal line is getting wrapped into a circle almost, right?
Yeah.
Of this smaller radius. So each of these lines is getting kind of wrapped into a circle where, we have this kind of picture where it's not a full circle, but it's basically a circle up to a measure 0 set, up to a negligible set. So it's not going to affect the integral. Right. If I integrate some function over this domain versus if I integrate it over a circle, the integral won't change.
Right.
Right?
Yeah.
Okay. So now, what would be the determinant of this transformation, of the Jacobian? Okay. So if we just look at the Jacobian, let's say d r theta, so we fix a point, and then we look at this Jacobian, and this is going to be the matrix. Well, okay, let's take the derivative of the first component with respect to the first variable, so cosine theta, and then derivative of the first component with respect to the second variable, so negative r sine theta. Similarly, take the derivative of g with respect to g2 with respect to r, and we get sine theta here, and then here we get positive r cosine theta, right? Which is the partial derivative of the second component with respect to theta. This is our Jacobian matrix. If we take its determinant, we just get r, right?
Yeah.
So we get r cosine squared theta plus r sine squared theta. So we just get r. Okay? And we'll just put the absolute value here. So what this means is that in terms of what this theorem is saying, this means that if I integrate, let's go ahead and put it up here. So if I integrate over the disk, which is the image of omega, so this is the disk here, of some function f over this disk, okay? So, and this is going to be in terms of my variables r and theta. But yeah, so let's just keep this like this. So we integrate that over the disk with respect to the Lebesgue measure dx, okay? And this is going to be equal to the integral over this box, which is parameterized as r and theta. The integral over this box of f of r cosine theta, r sine theta, r dr d theta, right? At disk, it should be, let's say we have coordinates on the disk, maybe x, y. Yeah? So this should be like f of x, y, dx, dy.
Right.
And then, correct? I think this is correct.
I think it's correct, but we just want from the box to circle, right? We want to go from box to circle, or we want to go from circle to box?
Yeah, good question. So I guess this integral here, yeah, we're starting at the circle. This is the image of our transformation. And then we're pulling it back. We're pulling the integral back to the box. So just in summary, the disk is going to have coordinates, Cartesian coordinates x, y. Whenever we're integrating with respect to the Lebesgue measure, we need to put Cartesian coordinates on our system, right? Because the Lebesgue measure assumes like a Cartesian coordinate frame. So then over the disk here, we have coordinates x, y. We have a function f, which is defined on the disk. So the function f takes in a value x, y on the disk and outputs a real number, right?
Okay, right.
And then the idea here is that based on this change of variables, G represents this change of variables which maps this open box into the disk. And the idea is that we can instead integrate over this box region, and this coordinates is r and theta, here, dr d theta.
Right.
And so we can just take f of g of r theta, which basically amounts to replacing the input x with r cosine theta, replacing the input y with r sine theta, right? And then we have to scale by this magnitude of this determinant, so r. And this is precisely the scaling that you see when you do polar coordinates.
Right, right.
So this is a vast generalization of polar coordinates, because this formula will work for anything, right? As long as you understand how to use it.
Yeah.
Okay, so it's a vast generalization. So I'm gonna put x here, but I think the key conceptual thing we need to keep in mind is that this x is a Cartesian coordinate in the image of omega, whereas this x is actually the Cartesian coordinate in omega, right? Okay. Yeah, so does that make sense?
Yeah.
Do you agree with that? Okay. So more generally, we have this, we have a Lebesgue measurable function f. Kind of not get too lost in the technical details of what it means for this function to be Lebesgue measurable. And really just say that you could think of f as nearly continuous, or in particular, like if I have a domain omega, okay, then the fact that, okay, so if this set is measurable, that what that means is that I can approximate it on the outside and on the inside by a covering of boxes, essentially. So I can take boxes in Rn, cover omega with these boxes, and approximate its volume, essentially by the volume of all these boxes. Okay? And let me just speed this up. Okay. So basically I can cut omega into a bunch of boxes, approximate its volume by the volume of those boxes. And moreover, if I want to integrate f, and f is measurable, then I can do the following thing. I can basically look at the set of boxes where f is nearly some constant value. So if f takes omega, say f takes omega into the real numbers, okay? Right? Then if I look at, let's say the real numbers, let's say here, okay? So if I look at some subinterval of the real numbers, the idea is that the pre-image f inverse of this subinterval, let's call this interval I, then the pre-image of I under the map f is measurable, which means essentially, hand-wavingly, that it can be approximated by boxes. By boxes. Okay? So what this means is that if I look at all the pre-image of where f maps the set I, it might be something like this maybe. Here. And then if I want to integrate f over this entire region, I want to approximate f. Let's say this interval is very small, so let's say that this goes from maybe a value a to a value a plus epsilon.
Right.
Then I want to approximate the value of f as just a on this interval.
Right.
So every one of these boxes, I'm going to assign them the value a under the map f.
Yeah.
So we'll say that f is approximately the sum AI indicator function of these ith intervals, okay? So what I'm going to do is, I'm basically this is going to be I here. This is the ith interval here. And then essentially I'm going to divide up the real line into a bunch of subintervals, okay? And I'm indexing them by I. And then each of these subintervals, sorry, this shouldn't be the indicator function of I, this should be the indicator function of f inverse. Okay? So basically, on each of the, have you seen this notation before?
No.
So this notation just means it's a 1 if you're in the set, and it's a 0 if you're outside of the set.
Okay.
Right?
Yeah.
So basically, I'm replacing, let's say, f, which could be maybe picture like f as being a surface over this kind of pulling out of the plane here. And then that surface is approximately a constant height on this region,
Right.
AI.
Yeah.
And so I'm going to replace f with literally a function that's constant, that's a constant height of AI on this set.
Yeah.
And then I'm summing over all these different sets.
Yes.
So basically, you could think about it as essentially replacing a surface with kind of like a bunch of level sets, almost like a staircase of level sets, right?
Yeah.
And that's an approximation. That's how we approximate the integral,
Right.
okay? And what we're going to do to integrate f is we're essentially going to look at the volume of this region. So we're going to say that the integral of f with respect to the Lebesgue measure, okay, is going to be approximately equal to the summation of the AIs times the volume of these sets. Fi, f inverse of these intervals, okay? So essentially, we're saying, okay, f takes the value AI on this level set. So I'm going to find the volume of this level set. I'll find the volume, and then I'll basically scale the weight AI by the volume of this set.
Right. Yeah.
And then if I sum over all these sets, I'm basically determining the net, like the overall or the average value of f.
Right.
Of course, weighted by the total volume of my region omega.
Yeah.
So in particular, if omega has total volume 1, then this sum will give me the average value of f. Right? And another way you can think about it visually is like by using colors. Okay, so another interesting visualization that I want to show you is like if you have for example, now let's look at a three-dimensional region. Okay, so what I'm saying here is that if omega is an R3, let's say, and here's my ambient space R3. Now I cut up omega into a bunch of boxes. And now they're cubes, right? And the idea is that if I perform this process, you can just visualize it in your mind, then the function f, let's say the function f assigns a color to every point. And we have some sort of color scale where maybe like blue is like the highest value of f, and red is the lowest value of f. And it kind of scales on a color scale.
Right.
Have you seen those plots before?
Yeah.
Right? So basically, we're going to color omega basically by the values of f. Then what we're saying is that we're going to decompose this omega into a bunch of cubes, and then we're going to approximate f as a fixed color on some subset of cubes. So maybe I have this level set of cubes is like red, and then this level set of cubes down here would be like orange. This level set of cubes would be like green.
Right.
And the idea is that I'm just going to approximate these levels as a fixed color, and that will allow me to get a good approximation of this integral, of the average color. And then as I use more and more boxes, right, and also finer and finer subintervals, this approximation will become more and more accurate.
Yeah.
Okay?
Yeah.
So that's the integration process that we need to understand in order to actually take these integrals. Okay? And notice that that the fact that omega is open, so omega being an open set makes it so that if I take any point in omega, it'll have a sphere around it. Or it'll have some sphere around it that's entirely contained in omega. That's the definition of being open. But I could also think about it as I can always find a cube. So around every point, I can find a small cube that's entirely contained in omega. Right?
Yeah, right.
Okay. So let's talk about how you might show this theorem and how you can prove this theorem. Okay. So the idea is that we want to look at small cubes, right? I've just described the integration process is essentially splitting everything into small cubes.
Yeah. So
now we need to focus in on each individual cube.
Yeah.
And look at how each individual cube gets changed under the change of variables g. What we're going to argue is that each cube is locally going to get transformed as long as it's small enough. It'll get transformed approximately by the linear map, which is the differential.
Right.
And so if it's perfectly a differential, if it's perfectly a linear map, it'll send a cube to a parallelepiped, right? And we're going to show that approximately it does this, okay? So yeah, and then I would say that one way of thinking about what we're trying to show here is like if you look at maybe one dimension for now, let's graph a function. So here's the graph of, let's say, a function f, where f is a function from the real line to itself. Okay? And we want f to be a C1 diffeomorphism, so it had better pass the horizontal line test. So let me just draw it better here, like that. Yeah. Okay. So now the idea is that locally, globally this function has some curvature, right?
Right.
But if I zoom in here, really close, then locally this function just looks linear. Yeah. Okay, I can approximate it by some linear function, which is going to be the differential. Okay, and then I can understand the mapping f as essentially a map which locally changes the volume of an interval, right? If I look at this interval, here's the interval I, and then an interval here, f of I, the image of this interval. And the idea is that this interval is going to get the volume distortion. It's going to change volume by a factor which is precisely the slope of this line. And the slope of this line is just the differential f prime in magnitude. Okay, so basically, if I look at the magnitude of this slope, it's going to tell me how much intervals are getting distorted. Right. But it's local, right? Because this is not a perfect approximation, as this curve has this has some curvature, right? So what we're saying is this actually holds in higher dimensional space. So in a higher dimensional space from Rn to itself, cubes are getting sent by this differential map, G. If this cube is small enough, it's getting sent to something that kind of looks like a parallelepiped. So maybe, let me draw this a little bit better. So if I have my true parallelepiped here, it's getting sent to something that looks pretty close to it, basically. That's what we're going to try to show. Okay? And then, so let's just quickly think about linear mapping. So if I look at a cube, if I look at just an ordinary cube sitting in Rn, okay? And the center will be the origin, okay? So the center of the cube is the origin of my space. And then I want to map this cube, let's say by a linear transformation T. So I give you a matrix T. Right. What will happen to the cube? Where will it go?
I mean, origin should be stay origin, and then we approximately we only have to care about the 8 points in the boundary, and then they might swap direction, but I mean they approximately looks like it, but it's maybe a shear, a little bit of shear. Yeah.
Okay, yeah, sure.
Yeah.
I agree with that. That's correct. Okay, let's say I gave you a matrix. Let's say I gave you a matrix A11, A1n, AN1 through ANN, okay? So how would you use this matrix to understand how the cube changed?
So you have to first set the coordinate maybe, and then just this t x x2 and and then maybe this is this is wire. This is general form, but I need numbers or actual coordinates to maybe if you want more steps J and then X. Yeah, but I mean like it's just more precise, but same deal. Yeah.
Right, okay, yeah. So this is going to be the matrix, the result of multiplying the matrix T by the vector X.
Yeah.
So I agree. I 100% agree. I want to think about this in terms of one specific concept, which is that if I view this cube in the following way, so let's look at the cube, and I said the center was the origin, right?
Right.
So what that means is that there's going to be a line through this cube, let's say. And let's look at there's going to be three principal directions, or three like coordinate directions.
Yeah.
So this line is going to be the coordinate direction given by E3. So like the coordinate direction 0, 0, 1, right?
Right.
And where does this matrix send that coordinate direction? It should just send it to the last column vector, right?
Yes.
So each of these column vectors is the image of the ith coordinate vector, right? So this coordinate vector is going to get sent to the third column of the matrix.
Right.
Okay? So that it's going to get sent to some line.
Yeah.
Right?
Yeah.
And that line will be the third column vector of the line will have direction given by the third column vector of the matrix.
Right, yeah.
So these three lines which define the cube are going to get sent to three lines in here. Let's see if I can draw this. Let's do these three lines. And then the idea is that if I look at these three lines, then they're going to cut out a parallelepiped. You see that?
Right, yeah.
So I'm going to end up with a parallelepiped. Okay?
Yeah.
And the parallelepiped will be framed by these three lines, which are the column vectors of the matrix.
Yeah.
Okay? So another way to say this would be instead of centering the cube, just put the cube to be spanned by the three unit vectors. So E1, E2, and E3 here.
Right.
And then, if I view the cube in this way, then I just need to look at the column vectors of the matrix to understand where they're sending this frame.
Yeah.
And they send this frame to some new frame, like this maybe, which should be T of E1, T of E2, let's say T of E3.
Right.
So these are the column vectors of the matrix.
Yeah.
And then this is going to form some parallelepiped.
Right.
Right?
Yeah.
Okay. So how do you find the volume? So this volume is 1, the unit cube. How do you find the volume of a parallelepiped?
So first we have to find the area. So so this is vector. And so that's the magnitude gives this area.
Right.
And then now you need the height but height, and then yeah, this one is actually perpendicular to this. So you need a projection. So 3. But you don't guarantee sign, so value. Yeah.
Perfect. Yeah. Okay. So I think this is pretty close. So yeah, if I'm getting you correctly, you want the area of this base, and the area of the base is going to be the magnitude of this cross product. Okay. And then you multiply by the height, which is the projection of this vector TE3 onto the normal vector, like you said, project onto the normal vector, which is TE1 cross TE2, and I want the projection, for the projection to work, I need to make sure that this vector that I'm projecting onto is of unit length. So I divide by this one cross TE2. And then you can see this cancellation here. And you recover exactly the formula that you came up with for the volume, right?
All right.
Now, let me ask you a different question, because this is going to be important. So, what happens to the volume if I scale one of these vectors? What will happen to the volume? Let's say I scale this vector by a factor of lambda.
So it's linear. So it's lambda. If the volume is v0, then lambda v0. Yeah. So,
Right. So that's going to scale this distance by a factor lambda, the projection, right?
Yeah.
I'm not adding a length lambda. I'm literally scaling this by a multiple of lambda. That'll scale this projection by a multiple of lambda. So it'll scale the volume by lambda, right?
Right.
What happens if I, let's say, translate this vector along the plane, right? If I move this vector anywhere along this plane here, which is the plane spanned by the other two vectors. So if I move this, consider the plane spanned by the other two vectors, and let's say I move this vector anywhere in that plane, what happens to the volume?
0.
It doesn't change, right? It doesn't change because it's going to keep the projection in the normal direction. So I'm free to move this vector anywhere on the plane, like I can basically attach a plane to the tip of this vector, which is parallel to the plane spanned by the base of the parallelepiped. And I can move this third vector anywhere on that plane, it won't change the volume. Right? And what that's saying is that I can add to this vector, I can add any linear combination of these two vectors and not change the volume. Okay? Yeah? And then there's a third thing that I can do. I can switch two vectors around. If I switch two vectors, it doesn't change the volume, obviously, right? Okay, so let me just pose to you an interesting fact here, okay? So if I look at any matrix T, okay, which is going to be some A11 through A1n, AN1, ANN, okay? And I want this to have a non-zero determinant, okay? Then if determinant of T is non-zero, then I can row reduce this matrix to the identity, right? And each of those row reductions is an elementary transformation. I can do elementary transformations of the following type. So I can do just a scaling of one of the vectors. So I scale one of the vectors by lambda. I can also apply an elementary transformation where I swap. So let's say I swap. Let's say I have swapping two rows, for example. So this represents the swapping of two vectors. And then, or I guess the swaps two columns. And then the third thing that I can do is I can essentially let's add in 1 and then let's add in a 3 here maybe. So let's just look at pretend we have some columns here and some rows. Then I'm going to take this column multiplied in this row.
So one component get more weighted.
Yeah, so this column is going to get maybe multiplied by 3 or something, right? As I move this row down in the matrix of multiplication.
Yeah.
And that's going to add on to this column. So yeah, this column of the resulting matrix is going to be the previous column of the matrix plus 3 times the column to its left. Right? Does that make sense?
Yeah.
So I'm basically, what I'm doing here is I'm taking one of the column vectors and I'm adding a scalar multiple of a different vector to it.
Right.
That's the transformation we described of like moving the third vector on the plane spanned by the other two.
Yeah.
Okay? So let's look at these. So these are the 3 types of elementary transformations. And they're exactly geometrically what I described earlier, where this transformation, scaling by lambda, is taking one of your vectors and scaling it up.
Yeah.
This is just switching 2 of the vectors. And this one is adding a some combination of one of the other vectors onto that vector, right?
Yeah.
Make sense?
Yes.
So, with these 3 elementary transformations, you can decompose T into a product of these types of matrices.
Yeah.
Now, the volume of the parallelepiped spanned by T is just going to be, actually, it's the value of its determinant, okay?
Right.
And the reason why is because if you look at the determinant of these 3 matrices, this determinant is 1, okay? This determinant is plus or minus 1. It might not be a perfect one, but it's plus or minus 1.
Yeah.
This determinant is lambda.
Right.
Okay?
Yeah.
So when I decompose the matrix into these elementary transformations, so let's say T is equal to E1, E2, etc., En, okay? And I take the determinant.
Right.
Then the determinant of T is going to factor into the product of these determinants.
Right. So,
And we just said that the only way that the determinant of T, or the only way that T can change the volume is through any of these scaling processes.
Right.
And so the scaling processes are going to be picked up by these determinants, and then any other process that doesn't affect the volume is just going to go to plus or minus 1 here. So in fact, by viewing T as a composition of elementary transformations, we can recognize that the determinant of T actually measures the signed volume of the parallelepiped.
Right.
And it'll be negative if the frame is not right-handed, right?
Right.
So like, if it changes the orientation of the frame.
Yes.
But the volume will just be the magnitude of this determinant.
Right.
So if I look at the magnitude of this determinant, this is the volume of T acting on the unit cube.
Yeah.
Okay. All right. And in fact, any cube, right?
Yeah.
If you apply the linear transformation T to it, its volume will get scaled by the magnitude of the determinant.
Right.
The linear
Right.
transformation.
Yeah.
Okay?
Yeah.
So the magnitude of the determinant measures the volume distortion of a linear transformation.
Yeah.
And so we can see here that this determinant in our theorem is measuring the local volume distortion predicted by the differential, which is a linear map, right? A matrix of the partial derivatives.
Right.
So basically what we're saying is that G, we can approximate it locally as a linear map, which is the Jacobian matrix. And that linear map, we understand its volume distortion, which is precisely the magnitude of this determinant.
Yeah.
Okay?
Yeah.
So that's the heart of the theorem. And that's what I want to show you how to prove, because it's not obvious, right? It's not obvious that, I think that it's a bit easier to understand how a linear map changes volume.
Right.
But G is not linear, it doesn't have to be. Right?
Yeah.
So it's not obvious that this approximation should work at all.
Yeah.
Okay? I want to approximate this integral in a compact set.
Right.
Okay?
Yeah.
And so let's just let E be a subset of omega be compact. Okay. And my idea is that I want this set E to basically be the approximate the total value of the integral.
Right.
Okay. All right. Now, so now since E is compact, we know that this partial. So the partial derivatives of G, let's say Gi partial xj, these partial derivatives are all continuous. Continuous on the compact set E, right? So this means that they are actually uniformly continuous. Okay? So, because they're continuous over a compact set.
Right.
So, what I can do is I can find, so for every epsilon greater than 0, there exists a delta greater than 0 such that the magnitude of partial Gi over partial xj at a point, let's say x, minus Gi over partial xj at a point y is less than epsilon whenever x minus y is less than delta and x and y are in E. Right?
Yeah.
Okay. So in particular, this delta is like uniform, right? It doesn't depend on it doesn't depend on the choice of x and y. Okay.
Yeah.
So I want to make a statement about the Jacobian matrix and how it changes in a small region. Okay. The Jacobian matrix itself. So this is the matrix partial Gi over partial xj. Okay.
Yeah.
Now this matrix, of course, is evaluated at a point x in my domain. Okay.
Right.
And if let's say I consider a small portion of the domain, and I have a point x and a point y in this small region, okay, then I want to understand what is the most distortion this matrix can have, okay? And I want that in the following sense. So if I take this, okay, this is going to be mapped by G, but what I really want to think about is this matrix, let's say dxg and dyg, okay? So these are the two Jacobian matrices of these two different points. And basically this matrix is going to take a vector in, let's say, Rn, okay? And it's going to map it to a new vector.
Yeah.
Okay?
Yeah.
Now if I take the same vector in Rn and I apply this matrix, it's going to map it to a slightly different vector.
Right.
Okay?
Yeah.
And I want to understand how close these two vectors are, given x and y are within epsilon distance.
Right.
Okay? Okay, so we have dxg minus dyg acting on a vector v, and this is going to be the sum over I and j of this partial Gi partial xj at x minus partial Gi partial G or partial x j y, and then here we have a v j ei, right?
Yeah.
Where ei are my basis vectors in Rn.
Yeah. What is V again? V
is just an arbitrary vector.
Okay. Yeah.
V is just an arbitrary vector in Rn, and these are just linear maps. So we're just looking at the difference between how these two linear maps take one vector.
Yeah.
Okay. And the idea is that that all of these I can bound uniformly to be less than epsilon. Okay.
Right.
So this is going to be less than or equal to or this is going, if I look at the norm of this thing, the norm of this, okay? The length of this vector. The length of this vector is going to be less than or equal to some constant times epsilon.
Yeah.
Right? I guess constant times epsilon times the magnitude of v.
Yeah.
Would you agree with that?
Yeah.
Okay.
Yeah.
Right. So I believe this is the correct interpretation. Of course, we need to bound above by the magnitude of v, clearly. But then all of these I can bound to be less than epsilon.
And then just triangle inequality.
Triangle inequality, exactly. Okay. Yeah, and then this is just a constant. This constant is independent. This is completely independent of my choice of delta too. Right. This constant only depends on
xy.
On the size of Rn. Honestly.
Yeah.
I don't even think it depends on a uniform bound on the partial derivatives. Okay.
Right.
Okay. So we have this bound. Well, let's interpret this real quick. Is that if I'm sitting in my domain, let's say this is a cube in omega, okay? And this is a small cube of side length epsilon, okay? And I have 2 points x and y. Then if I look at just the differential map dx of g and dy of g, then if I look at how where they send this cube, okay? So they're going to send this cube to, let's look at one vector in the cube. Let's look at this vector, okay? Take one vector in the center of the cube. They're going to send that vector, maybe dx, we'll send it somewhere here. So here's maybe the image of dxg. And then dyg is going to send it to a new vector, which is within epsilon distance of this vector, okay? So here's my vector v, here's dxg of v, and then all possible vectors within constant epsilon distance of this vector could be the possibilities for dy. So maybe dy is somewhere over here. Here's dy of g of v. Right?
Yeah.
But the point is that wherever dyg sends v, it'll be some vector in this sphere. Where this sphere centered at xg of v, this sphere has radius constant times epsilon.
Yeah.
Does that make sense?
Yeah.
Okay. So we see that the differential is behaving similarly inside of a small cube, and it's behaving similarly in this exact error approximation.
Yeah.
Yeah? Look at the cube. Let me draw the cube as a bit smaller here. And I take the center of the cube here, okay? Let's call the center of the cube x, okay? Now, I want to understand where g sends this cube, okay? So g I'm going to draw in green. G is not a linear map, right? So it might send the cube to somewhere weird. Okay? However, let's think about actually how to figure out where g sends the cube. If I do my previous analysis like I showed you for the linear map, if we take, let's just take a line in this cube. So I could take any line, but let's just start off with this vertical line here. Draw the back of the cube. Okay? So let's start off with this vertical line here. And let's look at where g sends this line. So, first of all, where does dxg? Dxg sends this line to, of course, the third column vector of the Jacobian. And it's just going to be, overall, the cube is going to get sent to a parallelepiped, as we discussed already, because the differential is truly a linear map.
Yeah.
Okay? Yeah. And this line might get sent to a line like this. Okay, and it'll get sent to a true line. Okay, where if this line has direction vector v, let's say, and goes through the point x, then this line will have direction vector dxg of v, okay?
Yeah.
Now, where does g send the line? Well, we don't know, but we do know one thing, that g is going to send this line to a curve, okay? So it'll send it to some curve. Let's draw the curve like this, okay? However, the tangent line to this curve, has to be this vector dxg of v at the center, okay? So let me draw this bigger. So this is the key point that you have to understand. Better for our understanding if we do it in 2 dimensions. So now let's just take a box, and we have the center point x, and we have some line in the box with direction vector v. Okay? Now, this box is going to get mapped by the differential dx of g into a parallelepiped Okay?
Yeah.
This line is going to get mapped to a new line, maybe like this, where this is dxg of v, the direction of this line, is the image of v under this linear map.
Right.
And, okay, but now, where does g send this line? So g is going to send the same line, okay? It'll send it to a curve, which might not be a perfect straight line. It'll send it to some curve. Let's see if I can draw this. It's hard to draw, but okay. Let's say it's this curve here.
Yeah.
And of course, it's not a straight line.
Right.
But the tangent vector to this curve at the center point, x. So this is g of x here. The tangent vector to this curve must be the image of the differential.
Right.
Okay? Yeah. And moreover, if I zoom into this curve here, okay, and I think about every tangent vector on this curve, okay, then every tangent vector, let's say at a point g of q, where q is going to be some other point on my line, the tangent vector at g of q is the image dq of v. Of the differential, dq of g of v. So the tangent vector at every point along this curve is the image of v under the differential map, which is the Jacobian map at that point. Okay? So what do we know about the image, the tangent vector, how this tangent vector can change? Well, as we discussed, right, the image of v under this Jacobian can only change within a small sphere. And that small sphere has radius constant times epsilon. Okay? So we have a curve here in green, which is the image of this line under G. And this curve has a tangent vector, which always is of the form, which is always, sitting somewhere inside this sphere. Okay? So every tangent vector of this curve is within epsilon, constant times epsilon distance of the tangent vector dx of v. Does that make sense? So essentially, what this means is that the distance between the green curve and the orange line is increasing at a rate. It starts off at 0. The distances agree at the center. And then the maximum error, the maximum distance between these two curves is growing, can at most grow at a linear rate of c times epsilon. So at the end of the day, this error here is growing at a rate of c times epsilon, and it grows over a distance which is also a constant multiple of epsilon, right? So if the side length of this box is epsilon, then the length of this line here is also a constant times epsilon. Let's say a different constant.
Yeah.
Okay? So I have a length scale, a distance scale that's of order epsilon, and then I have an error, which is the error between the line of the parallelepiped and the true green line, which is the image under G.
Yeah.
That error is growing at a rate at most epsilon.
Yeah.
So in particular, the net error must be an order of epsilon squared. Right? Because it's growing at a rate of epsilon over a distance that's epsilon.
Right. Yeah.
You agree with that?
Yeah.
So that means that the final point of this curve, so this endpoint here, has to be within epsilon squared of the parallelepiped. Let me draw this one more time. Let me just draw it out a little bit better. Okay, so in summary, this is the most important and most difficult part of the proof. So basically, we have taken this parallelepiped, which is the image under the differential map, and then we've argued that the true line, the true curve, okay, which is the image under G, that true curve has tangent line, has a tangent vector, which always belongs to essentially this sphere.
Yeah.
Right?
Yeah.
So if I go somewhere else on the curve, like here, like this point Q,
Yeah.
my tangent vector is always within a sphere of the tangent vector that I described as the image dx. This is dxg of v. Okay?
Yeah.
And then because of that, because this tangent vector is like almost constant, it's only changing by a factor of epsilon, the distance between these two lines starts at 0 and grows at a rate at most constant times epsilon.
Yeah.
And it grows over a length scale, which is a constant times epsilon. Because this length scale, the length of the parallelepiped, is also of order epsilon.
Yeah. Yeah.
So that tells me that the ultimate error between not just the image of the vector, but the error between the actual boundary of the parallelepiped and where G maps that point on the boundary, this error is actually of order epsilon squared.
Right.
Right?
Yeah.
Okay, so what I can do using this analysis is essentially show that I can do this for every point on the boundary of this cube. And what that's going to do is it's going to cut out a boundary of the parallelepiped. So basically just picture like taking this sphere taking a sphere centered at this point on the boundary of the parallelepiped and just tracing it out everywhere on the parallelepiped.
Right.
And that's going to create an epsilon squared neighborhood of the parallelepiped.
Yeah.
And the true image of this cube under G must lie within this epsilon squared neighborhood of the parallelepiped.
Yeah.
So that tells us that we have some bound, if we use the volume of the parallelepiped as an approximation for the true volume of the image of this cube under G, we're going to be of an order of error which is highly accurate. We can go into the specifics of that error. Okay, a cube of side length epsilon, okay, is going to get mapped. Okay, I map it first under the differential, and that's going to map it to a parallelepiped. And then I know that the true image under G is something weird, right? It might not be a perfect parallelepiped. It's going to be something a little bit weird. However, it's trapped within this kind of neighborhood, this epsilon squared neighborhood of the parallelepiped, okay?
Yeah.
And so what we want to ask ourselves is what's the maximum error of the difference between the volume of the parallelepiped, which is our approximation, and the volume of the true image under G.
Yeah.
What is the difference between those two volumes? And to understand that difference, we can bound it by the difference in volume between the inner parallelepiped and the outer parallelepiped, right?
Yeah.
Okay?
Yeah.
Now that distance, remember, this distance is epsilon squared.
Yeah.
Okay? So the inner parallelepiped is going to have a volume which is proportional to its radius, which is epsilon minus epsilon squared to the n, okay? So we've taken the orange parallelepiped, which has side length of order epsilon.
Yeah.
So the inner one has side length of order epsilon minus epsilon squared.
Yeah.
So its volume is proportional to this to the power n.
Yeah.
You agree?
Yeah.
And then the volume of the outer parallelepiped is proportional to epsilon plus epsilon squared to the n.
Yeah.
Okay? So then if I look at the error here, it's going to be the volume of the outside minus the volume of the inside.
Yeah.
And then this is going to be epsilon plus epsilon squared, let's say, to the n, minus epsilon squared to the n.
Yeah.
I take the lowest power of epsilon, because we're assuming epsilon is small. And so this is order, yeah, so it's actually epsilon. If I expand this out, the epsilon to the n terms will cancel. And I'm left with an epsilon to the n plus 1 term. So the order of the error is epsilon to the n plus 1.
Yeah.
You agree?
Yeah.
Okay. So what that tells me is that for a small epsilon, the difference in the volumes between the true image of G and the image under this differential map is of order epsilon to the n plus 1. Okay? That's going to be my error in my volume approximation. In fact, F is defined on G of omega, not omega. So let's say this is G of omega, and omega is here. So yeah, so F is actually defined on G of omega. And this is sending us into the real numbers. Yeah, so we have this mapping G here, and we understand how it affects a small cube in omega. It's going to send that small cube to approximately something which we can kind of estimate to be a parallelepiped, right? Okay, and the idea is that that if I want to integrate F over this G of omega here, what I can do is I can slice omega into cube length of side length epsilon, okay? So let's create an epsilon partition of omega. Then look at where this epsilon partition goes under the map G, okay? And this is going to go to some partition like this, which may not be fully Cartesian anymore, but it'll go to some partition like this of G of omega. This is still a partition, right? And I'm assuming implicitly that omega is compact here, because ultimately we want to do the approximation of a compact set. Then this grid is going to get, because G is going to be uniformly continuous on any compact set. So let's say this is actually E subset of omega compact. Okay? And this is G of E. So since G is uniformly continuous here, what that means is that if this grid gets finer and finer, then this grid will get uniformly finer and finer.
Yeah.
So this is a valid partition of our space that we can integrate over. Okay? And if I want to integrate the function f over this partition, then again I'm going to look at its level sets. So I'm going to say, well, the value of f is approximately 3 maybe here, right? Say f is approximately 3 on this level set, and then maybe f is approximately 4 on this level set, etc. And then I'm going to sum the values of f over that level set, weighted by the volume of that level set. Okay? Yeah, let's say that that this is my level set, then I'm going to have the sum of, let's say, 3, or let's say the sum of the value of f, and then the approximate value of f multiplied by the volume of the level set, right? Okay, so if I want to integrate with respect to this partition, right? The integral shouldn't depend on the partition of the space, right? As long as you partition finely and finely enough, the integral will be correct, right?
Yeah, converge.
So if I want to integrate over this space, this is the integral of g of omega of f of x. Okay? So this is the integral that I'm trying to compute. I'm going to, let's partition omega into cubes ci of radius epsilon, okay? And this set of cubes is going to run from 1 to n. It's a finite set of cubes, but we're going to note that n is going to scale as 1 over epsilon to the n, right? Because as I shrink epsilon, I'm going to need that many more cubes, to fill the region. Agree? We want to integrate over g of omega, right? So what we're going to do is we're going to take all the centers, we're going to view this as our partition, g of omega. We're going to take all the centers of these cubes or these parallelepipeds, okay? And the centers of these, let me just be clear here, that this partition is not a perfectly linear grid anymore. It can look kind of crazy.
Yeah.
And now I have centers, let's say xi here, or g of xi, let's say. G of xi. And I have centers for my partition, which are these kind of g of these cubes, these ci's. Okay, right?
Yeah.
So if I want to integrate f over g of omega, okay, then I'm essentially going to want to, if this was a Riemann integral, I would take the sum over this partition, so over I, running from 1 to n, and I would take the value of f at the center, g of xi, and then multiply by the volume of this region of the partition. So that's the volume of g ci.
Yes.
Okay?
Yeah.
Now, this is equal to the sum from I equals 1 to n of, f of g of xi. Now, volume of dxig applied to ci, okay?
Yeah.
Plus our error in this approximation of this region by a parallelepiped.
Yes.
And that error, we said, is of order epsilon to the n plus 1, but then this is multiplied times n. So multiplied by n, right? Each element of this sum accumulates that error. Epsilon to the n plus 1.
Yeah.
But n is of order epsilon, 1 over epsilon to the n.
Yeah.
So ultimately, this order of our error is order epsilon.
Yeah.
So it's a good approximation.
Yeah.
It'll as we said, epsilon to 0,
Yeah.
it'll go to 0.
Yeah.
But then this is precisely, okay, so this is plus order epsilon,
Yeah.
and this will go to 0 as epsilon goes to 0.
Yeah.
Well, then this term here is precisely the integral. And now we can think of this volume of dxigci. This, as we've shown, is just determinant of the magnitude of the determinant dxig times the volume of ci, right?
Yeah.
So now we're summing over, let's write that out explicitly. We have the sum of f of g of xi times the magnitude of the determinant dxig times the volume of these cubes ci's. But this is an integral which is summing over the volumes of the cubes of ci, so that's an integral with respect to this partition, with respect to omega.
Yeah.
This last sum is precisely this integral on the right hand side.
Yeah.
right? Do you agree with that?
Yeah.
Okay, so that's how you do it in the Riemann integral case. And then for the Lebesgue integral case, you can do the same argument. This is still the crux of the argument. And then you're just going to add some limiting process and be a bit more technical with, you're going to start with a compact set, and then the level sets of F you're going to approximate by certain collections of cubes. So essentially, what you're going to do is take a sequence of functions which are Riemann integrable. You're going to be able to find the Riemann integral via this construction. And so it's like, almost think of it as a sequence of rational numbers that converges to a real number. Then this function f, you're basically going to be able to find a sequence of Riemann integrable functions which converge to the function f in this, with respect to this L1 metric. And then all this analysis will hold when you pass to the limit. So really this is the crux of the analysis here. And the key thing is that our order of the error in the approximation of the parallelepiped with the true image was of order epsilon to the n plus 1. So it's actually getting a better and better approximation the smaller cubes you make, right? Which is not obvious, right? Because you might think that, the cube shrinking means that even though you have smaller error, you have smaller total volume. So the ratio to your volume, your error to volume ratio might not actually be decreasing. It could be constant, for example. But in this case, the error to volume ratio, in the scaling, it actually works out to be order of epsilon. So when you scale down to smaller and smaller cubes, they truly are getting closer and closer to being mapped to parallelepipeds, which are the image of the differential. So locally, the differential of a function really represents how that function distorts mass from a small cube to a small parallelepiped. And that approximation gets better and better and better the closer you zoom in. So this is just a higher dimensional analog of, like, if you view a curve, a smooth curve, and you zoom into it, eventually it'll just look like a straight line. Right? If you view the map G and you zoom into the map G, eventually it'll just look like a linear transformation given by the Jacobian map. So what do you think? Do you have any questions, or did it all make sense?
So eventually we are comparing between the true transformation and then the differential linear transformation, and then we see the difference, and then if the errors goes fast enough or the errors goes as epsilon or higher order, then we are good.
So essentially, so I mean, the error is associated with, right, you want to understand the volume distortion of G, and you want to approximate that volume distortion as basically the parallelepiped, right? And the error is coming from the difference in the volume of the parallelepiped to the true image of a small cube under G. And so that difference, the difference between the volume of the parallelepiped, the volume of the image of the cube, is of an order epsilon to the n plus 1. The problem is that it might be that you're going to accumulate error over more and more cubes, because when you do the partition, when you do the integral over a finer and finer partition, you're going to have many more cubes that you're approximating over. And so you could be accumulating error. But the number of cubes in the integral is increasing like 1 over epsilon to the n, right? Like if I divide a cube of side length 1 into cubes of side length epsilon, I'm dividing it into 1 over epsilon to the n cubes. And so the amount of net error in the approximation scales as epsilon to the power 1. Epsilon to the power 1, right? We have this epsilon to the n plus 1 multiplied by 1 over epsilon to the n. So we get a net error which scales like epsilon. So as I make epsilon smaller and smaller, the overall error in my volume approximation is going to 0. So it's essentially, the tangent line is an approximation of a function up to second order, right? Like if you subtract a tangent line to a function, the error is going to be second order. With respect to epsilon, because you're subtracting the first derivative, right? That's how it should be.
So it's actually like a good best linear approximation actually.
Yeah. The Jacobian is the best linear approximation at that point. Yeah, exactly.
Yeah.
So it literally is a higher dimensional version of the tangent line approximation.
Cool.
Yeah.
Yeah, actually, it's not just one approximation, but it's best approximation.
The best approximation.
Yeah.
And then, you can use this to calculate different coordinate systems. So say you had a specific problem with a certain symmetry, and maybe that symmetry wasn't spherical or cylindrical symmetry. Maybe it was a different type of symmetry.
Freaking torus.
Yeah, toroidal symmetry or some other symmetry that you wanted to exploit.
Yeah.
You could use this change of variables to construct your own new coordinate system, and you can understand exactly how to calculate that integral.
Yeah, that's very useful.
Yeah.
Especially when you cannot visualize the coordinates. More than 3 dimensions.
It also just gives you an intuitive understanding of how a mapping, how a C1 diffeomorphism is changing the volume of a space locally, right? We always think about the derivative as like a tangent line or something.
Right.
But another way to see the derivative is it's a local stretching factor. So if I have a function from the real line to itself, the derivative measures how much the line is being stretched or compressed locally.
Right.
And this is a higher dimensional version of that, where the magnitude of the determinant of the Jacobian measures how much n-dimensional space is getting stretched by the map G. And it's not just how it's getting stretched. We also know the directions how it's getting stretched in which directions, right?
Yeah.
Like this parallelepiped, framed by these by the gradients of each of the component functions, right? The column vectors of the Jacobian. The frame of that parallelepiped is exactly, telling us how space is being transformed by the mapping G locally.
It's not just like scaling factor, but it tells us the direction also.
So it's basically saying that a C1 diffeomorphism preserves a lot of information about volume.
Right.
And we can know a lot about how it changes the volume of a space. Right?
Maybe it can be used as first we start with maybe like cube, and then maybe we deformed, but the deformation is not uniform. Like some part is like deformed drastically, like maybe like for space-time like a neutron stars, and then some place up far away it's almost like no deformation at all. Then maybe with this computation we can actually detect which part is most deformed.
Yes, exactly.
Exactly.
Right.
Maybe we don't even need to integrate whole space. We just want to find which one is the interesting part.
Yes, I agree. I agree. So to detect specific regions of space, we can use this function f here, right? So f, we could pick f to be a bump function that is centered around the region that we care about.
Right.
So say I only care about understanding the sphere. Then I can choose f to be the value 1 on the sphere, and 0 outside of the sphere. And then I can understand how to integrate over that sphere just by essentially using a bump function. But you're right. It's important to recognize that we're not just considering maps of Rn to itself. We're considering any open subset of Rn getting mapped to another open subset of Rn. I think it's the spherical coordinates is a cool example, right? If we go back to that example real quick. So we had this square, which was in the theta r plane, and here is 0 and 2 pi. And so each of these lines are going to get mapped. Let me use colors here, okay? And then this line is getting mapped into by the function g. Remember, a function g sends r comma theta to r cosine theta, r sine theta,
Yeah.
then this first line here is going to get mapped to kind of a smaller circle, like this.
Yeah.
The next line, the pink line, is going to get mapped to a larger circle. And then the orange line will get mapped to an even larger circle.
Yeah.
Okay?
Yeah.
And now if I look at a small box here, let's look at this small box here. This small box, like what you said
Yeah.
earlier, right?
Yeah.
Where is this small box going to get mapped to?
Yeah, so 1, 2, 3. So 1, 2, 3, and then yeah, it's a little bit up there and yeah, or 2 pi. You see here.
Yeah. But if we look at what this small box actually looks like, it's not a perfect box.
Yeah.
It's actually
Because R changes a little bit. Yeah.
it's actually
Like
a piece of a wedge,
yeah.
right?
Yeah.
Piece of a wedge.
Yeah.
We're approximating this, the area of this wedge. So this area will be dx dy, right? Then the area of this wedge we're approximating to be, again, the determinant of d.
Actually, that's dr d set.
Okay, so this is the problem, is that this is why we need to be careful, is that I actually want to view
Yeah.
like I think r and theta are confusing.
Yeah. Yeah.
This is just a plane, and I'm using Cartesian coordinates to understand this plane.
Right.
So this is a Cartesian system that I'm applying to this plane here.
Yeah.
Now, when I map this through under G, then I get a region whose area, let's use the same coordinates now, x and y here.
Yeah.
Then this region will have determinant d x comma y
Yeah.
g in magnitude times dx dy.
Yeah.
Okay?
Yeah.
And now x and y I can really think of as r and theta,
Yeah.
right?
Yeah.
So we can go ahead and call them r and theta, but we're kind of thinking about them differently now. We're thinking about them as Cartesian coordinates, right?
Yes.
In this plane.
Yes.
So here's dr d theta, and then here is dr d theta.
Yeah.
We already calculated this determinant.
Yeah, that's R. Yeah.
It's r,
Yeah.
okay? So this is just equal to r dr d theta. And so what I'm saying is if I want to integrate a function over this region, if I want to integrate a function over this region, say the function f, which sends this region to the real line, okay? Then call this g of omega here. And my integration is done with respect to these coordinates x and y here, right?
Yeah.
Then I can pull this back. I can pull this back under the change of variables g.
Yeah.
When I pull back the function f, I get f composed with g,
Yeah.
which is a map from this plane now into the real line. This is f composed with g, called the pullback. And now I integrate this function f composed g, okay, over the region omega, but now I need to scale this volume actually by this the magnitude of this determinant.
Yeah.
This is r. So now g of r theta r dr d theta.
Yeah. Yeah.
And that's exactly polar coordinates here.
Right. Right. Yeah.
Right? So if I'm using the coordinates r and theta to describe, to ultimately describe, like I have some symmetry with respect to like rotational symmetry or something, so I want to use polar coordinates,
Yeah.
then I need to account for the fact that polar coordinates are distorting volume.
Yeah.
And they're distorting volume in exactly this way, well, this approximate way. This isn't a perfect approximation because we're really approximating this as a as a parallelepiped.
Yeah.
Right?
Yeah.
But that error is going to go to 0 when we pass to the limit, or to the integral.
Right. Yeah. Yeah.
Yeah, so I mean, before I studied this theorem, I felt like I just memorized
Right.
a lot about integration, right?
Yeah.
Like,
It's like I don't think about it.
yeah, like in an undergraduate class, I mean, you're just handed this formula,
Yeah.
a simpler version of this formula.
Yeah.
You were just handed it and never really had to question it.
Right.
And it's really non-trivial because this is a non-trivial approximation, right?
Yeah.
Like we really have something. This box is no longer a box
Right.
in polar coordinates.
Right.
So it's not obvious that this approximation via parallelogram actually works.
Yeah, if you use the same integration when you put the limit side, it's not obvious. Yeah.
It's not obvious at all. And I think that, a lot of times we just do the calculation and, go to polar coordinates, use r dr d theta or r squared sine theta dr d theta d phi without thinking about where the theorem came from or why it's true, why it works.
Yeah.
So I think over the past few days, really thinking about this theorem and understanding the proof behind it really changed my perspective on integration and change of variables, right?
Yeah.
And it's important to also recognize that this can go both ways, right? G is a C1 diffeomorphism, so it's invertible, and its inverse is also a C1 diffeomorphism. Okay, so I can go either way here and apply the same logic. In particular, if I compose this again with G inverse, right?
Yeah, it should work.
Then I'm going to get determinant of dxg, determinant of G inverse at G of x, and these are going to cancel and become the identity matrix. And so I'm going to get back over here.
Oh, yeah.
Right? Does that make sense?
Right, yeah.
So it's kind of a symmetric, it doesn't seem symmetric, but I can go back and forth by composing with G inverse as well.
Yeah, that's
right.
Yeah, that's the important part.
Yeah. So. Right. I feel like the most beautiful part of this theorem for me was when you look at the sphere, right? And you basically see that G maps a line to a curve, but the tangent vector to that curve has to always be close to the image of the vector under the differential.
Yeah.
So because that tangent vector is not changing too much, the curve itself is constrained to lie within a cone. Actually, let me add this piece of intuition that I wanted to share with you, because this is also super cool. If we go back to the key part of the theorem, like the part of the theorem that makes everything work, right? We had this cube and a line through the cube. Now this line, if I just view it as the linear transformation, right, I get a new line in a parallelepiped. Okay. So the true mapping G maps this line to a curve. It will be some curve. Well, let me make this more accurate. It's going to be a curve which definitely passes through this point and is tangent to this line at this point. So it might look something like this, maybe? Okay? And the idea is that so if I look at this tangent vector frozen on the curve, this tangent vector frozen on the curve, and I just move along the curve and look at its tangent vector, it will always be of the form, it'll always be something like this vector, but within a sphere of radius epsilon. Okay? So if I take my curve here, then at every point I have a tangent vector, and that tangent vector is within some sphere of this original tangent vector. Right? Okay? And so the idea is that actually traps this trajectory, and it traps the trajectory in a cone, in a literal cone, centered around this line. And the cone, which traps the trajectory, the true trajectory. This is very related to general relativity, by the way.
Yeah.
The cone which traps the real trajectory, so the real trajectory has to lie somewhere in this cone.
Right.
This cone, its endpoint is the radius of this cone is growing at a rate of epsilon over a distance which is a scale multiple of epsilon. So ultimately, this cone has a radius, has an endpoint, has a sphere at its end with radius epsilon squared times some constant. So the true image of this line here is just some smooth curve, we don't know what it is, but it's trapped within the cone. And it can't leave that cone, because if it did leave the cone, right, then think about leaving this cone. Then at this instantaneous moment when it leaves the cone, it's going to have to deviate from the line, and it'll have to deviate from the line faster than what's allowed by the allowable tangent vectors. Right? Yeah. So it essentially can't escape this cone. Isn't that beautiful?
Yeah.
And so we apply this process to all of the lines, all of the directions in this cube, which I can think of them as like all the directions, which I'm viewing G as like a map from, I'm kind of looking at the directional derivative of G essentially. And each of these lines is going to get mapped to some point that's trapped within this respective sphere. And then when I repeat this process everywhere, then I get some object, right? But that object is trapped within this neighborhood cut out by the spheres of radius epsilon squared. And so I can ensure that my approximation of this parallel pipette is quite accurate. And in fact, it's accurate in volume up to order epsilon to the n plus 1.
Right.
So that's the key part of the proof. I felt like that was really beautiful when I first thought about it, right?
It is pretty,
Yeah.